Welcome to the second lecture on electrical engineering fundamentals. In this lecture we will cover the following: resistors in series and in parallel, as well as the voltage divider circuit and current divider circuit. We will solve several examples and problems to illustrate each of these topics. Before talking about serially connected resistors, we will solve the following example to get a feeling about the meaning of resistors connected in series and the equivalent resistor. In the following example, we want to replace these three resistors R1, R2, and R3 between nodes A and B with a single equivalent resistor R equivalent without affecting the current I generated from the voltage supply. By applying KVL on the closed loop, we get minus Vs plus I R1 plus I R2 plus I R3 equals to 0, from which I equals to 2 amps. We can replace these three resistors with a single resistor between nodes A and B, where the equivalent resistor from equation 2 is given by R equivalent equals to Vs over I equals to R1 plus R2 plus R3 equals to 10 ohm. We notice that the equivalent resistor R equivalent is larger than R1, R2, and R3. Series connected circuit elements carry the same current. The resistors in the previous example, as well as the resistors in the circuit shown, are connected in series. We can show that they carry the same current by applying Kirchhoff's current law to each node. The series connection requires that Is equals to I1 equals to minus I2 equals to I3 equals to I4 equals to minus I5 equals to minus I6 equals to I7, which illustrates that if we know any one of the 7 currents, we know them all. So we can delete all the currents and leave a single current Is. To find Is, we apply Kirchhoff's voltage law around the closed loop, from which we get minus Vs plus Is times R1 plus Is times R2 plus Is times R3 plus Is times R4 plus Is times R5 plus Is times R6 plus Is times R7 equals to 0. From this equation, we notice that the 7 resistors connected in series can be replaced with a single equivalent resistor whose numerical value is the sum of the individual resistors. That is, R equivalent equals to Vs over Is equals to R1 plus R2 plus R3 plus R4 plus R5 plus R6 plus R7. In general, if K resistors are connected in series, the equivalent single resistor has a resistance equal to the sum of the K resistors. In other words, R equivalent equals to the summation from I equals to 1 to K of Ri. Note that the equivalent resistor is always larger than that of the largest resistor in the series connection. Now we will talk about resistors connected in parallel. In this example, we have two resistors sharing the same two nodes A and B and the same voltage. We want to replace these two resistors with a single equivalent resistor R equivalent without affecting the current I generated from the voltage supply. By applying KCL and Ohm's law, we get I equals to I1 plus I2 equals to Vs over R1 plus Vs over R2, from which I equals to 7.5 amps. We can replace these two resistors with a single resistor between nodes A and B, where the equivalent resistor from equation 1 is given by R equivalent equals to Vs over I equals to 1 over R1 plus 1 over R2 to the power -1, or R equivalent equals to the multiplication of R1 and R2 over the sum of R1 and R2. Note that R equivalent is equal to 2.67 ohms and is smaller than R1 and R2. Parallel connected circuit elements have the same voltage across their terminals. The resistors in the previous example, as well as the resistors in this circuit, are connected in parallel. Resistors in parallel can be reduced to a single equivalent resistor using Kirchhoff's current law and Ohm's law. From Kirchhoff's current law, Is equals to I1 plus I2 plus I3 plus I4. Since the resistors are connected in parallel, this means that they share the same voltage across their terminals. Hence, from Ohm's law, I1 times R1 equals to I2 times R2 equals to I3 times R3 equals to I4 times R4 equals to Vs, from which I1 equals to Vs over R1, I2 equals to Vs over R2, I3 equals to Vs over R3, I4 equals to Vs over R4. Substituting these equations in equation 1 yields Is equals to Vs times 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4, from which Is over Vs equals to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4 equals to 1 over R equivalent. For K resistors connected in parallel, 1 over R equivalent equals to the summation from I equals 1 to K of 1 over Ri. Note that the equivalent resistor is smaller than the smallest resistor within the parallel resistors. For just two resistors in parallel, R equivalent equals the product of the two resistances divided by their sum. Now we'll solve some examples to further illustrate the concept of resistors connected in series and in parallel. In this example, we want to find Is, I1, and I2. We start our solution by noting that R3 and R4 carry the same current, I2, and are connected in series. These two resistors can be reduced into one equivalent resistor, where R equivalent 1 equals to R3 plus R4. Now we notice that R equivalent 1 and R2 share the same nodes A and B, and thus are connected in parallel. These two resistors can be reduced into one equivalent resistor, with R equivalent equals to R2 times R equivalent 1 over R2 plus R equivalent 1. Using Ohm's law, Is equals to Vs over R1 plus R equivalent equals to 12 amps, from which we can find the voltage difference between nodes A and B, where Vx equals to Is times R equivalent equals to 72 volts. We notice that Vx is the voltage difference across the terminals of resistor R2 and R equivalent 1, from which I1 equals to Vx over R2 equals to 4 amps, I2 equals to Vx over R equivalent 1 equals to 8 amps. In this example, we need to find the voltage V across the current source, as well as the power delivered by the current source. We also need to find the power dissipated in R5. We begin our solution by finding the equivalent resistor for R4 and R5, which are connected in series. R equivalent 1 equals to R4 plus R5 equals to 16 ohms. Now the parallel resistors R3 and R equivalent 1 can be reduced to a single equivalent resistor, call it R equivalent 2, where R equivalent 2 equals to R equivalent 1 times R3 over R equivalent 1 plus R3 equals to 12.8 ohms. The two series connected resistors R2 and R equivalent 2 can be reduced to a single resistor, which equals to the sum of both, where R equivalent 3 equals to 20 ohms. The remaining two resistors R1 and R equivalent 3 are in parallel, with an equivalent resistor of R equivalent, which equals to 12 ohms. From Ohm's law, V equals to I times R equivalent, which equals to 60 volts. Since the current in the current source is flowing in the direction of voltage rise across its terminals, the power equation is written as P equals to minus VI equals to minus 300 watts. Since the power is negative, it means that it's being delivered. Hence, the delivered power by the current source is equal to 300 watts. In order to find the power dissipated in R5, we need to find the current flowing through it. In order to do that, we need to go back and find the current and voltage across each of the equivalent resistances. The current flowing in R equivalent 3 is equal to V over R equivalent 3, which equals to 3 amps. This is the same current flowing through R2 and R equivalent 2. Hence, the voltage across R equivalent 2, call it VCD, is equal to 3 times R equivalent 2 equals to 38.4 volts. This is the voltage between nodes C and D, and this is the voltage across R4 in series with R5, from which the current flowing in R5 is given by I R5 equals to VCD over R4 plus R5 equals to 2.4 amps. The power dissipated in R5 is equal to the current flowing in R5 squared times R5, equals to 57.6 watts. Now we will talk about the voltage divider circuit. Sometimes, especially in electronic circuits, developing more than one voltage level from a single voltage supply is necessary. One way of doing this is by using a voltage divider like the one shown in this figure. The two resistors R1 and R2 are connected in series and carry the same current I. Applying KVL on the closed loop, we get Vs equals to V1 plus V2 equals to I times R1 plus I times R2, from which I equals to Vs over R1 plus R2. By using Ohm's law, now we can express V1 and V2 in terms of Vs and R1 and R2. V1 equals to I R1 equals to Vs times R1 over R1 plus R2. V2 equals to I times R2 equals to Vs times R2 over R1 plus R2. Equations 3 and 4 illustrate that the voltage Vs is being divided between R1 and R2, where the ratio between V1 over V2 is equal to the ratio of R1 over R2. This means that the larger resistor will have a higher voltage across its terminals. In this example and for this voltage divider circuit, we want to find the maximum and minimum value of V output across R2, knowing that the resistors R1 and R2 used have a tolerance of plus minus 10%. In this voltage divider, and as was illustrated in the previous slide, the 100 volt is divided between R1 and R2, where the voltage across R1 and R2 depends on the ratio of the two resistors. The larger resistor will have a higher voltage across it. We know that V out equals to V times R2 over R1 plus R2. V output will be maximum when R2 is 10% higher, that is R2 equals to 110 kilo ohms, and R1 is lower by 10%, that is R1 equals to 22.5 kilo ohms. Substituting these values of R1 and R2 in equation 1, we get that the maximum value of V out is equal to 83.02 volts. V output will be minimum when R2 is lower by 10%, equals to 90 kilo ohms, and R1 is higher by 10%, equals to 27.5 kilo ohms. Substituting these values in equation 1, we get that the minimum value of V out is equal to 76.6 volts. In this example, we need to find the no-load value of V out. V out when the loading resistance is 450 kilo ohm. The power dissipated in the 30 kilo ohm resistor if the load terminals are short-circuited, and the maximum power dissipated in the 50 kilo ohm resistor. The no-load value means that the loading resistor is removed. In that case, V out equals to V times R2 over R1 plus R2 equals to 75 volts. The equivalent resistance of the parallel resistors R2 and RL is given by R equivalent equals to R2 times RL over R2 plus RL equals to 45 kilo ohm, from which V out equals to V times R equivalent over R1 plus R equivalent equals to 72 volts. When the load terminals are short-circuited, it means that all the current will flow in the short circuit and no current will flow in R2, so R2 can be neglected. The current is given by I equals to V over R1 equals to 4 milliamps, from which the power dissipated in R1 equals to I squared R1 equals to 0.48 watts. Maximum power is dissipated in the 50 kilo ohm resistor when maximum current flows through it. This occurs if the loading resistance is open circuit. From part A, I equals to V out over R2 equals to 1.5 milliamps, from which the power dissipated in R2 is equal to I squared R2 equals to 0.1125 watts. In the voltage divider circuit, we had a voltage source in series with the resistors. The current divider circuit, on the other hand, and as shown in this figure, consists of two resistors connected in parallel across a current source. The current divider divides IS between R1 and R2. Since the two resistors are connected in parallel, they experience the same voltage across their terminals, V. Applying Ohm's law, we get V equals to I1 R1 equals to I2 R2 equals to IS R equivalent equals to IS R1 R2 over R1 plus R2, from which I1 equals to V over R1 equals to IS times R2 over R1 plus R2, and I2 equals to V over R2 equals to IS times R1 over R1 plus R2. Equations 2 and 3 illustrate that the current supplied by the current source is being divided between R1 and R2. It shows that the ratio of I1 over I2 is equal to the ratio of R2 over R1. This means that the smaller resistor will have a higher current passing through it. In this example, we need to find the power dissipated in R4. In order to find the power, we need to find the current flowing in R4 by simplifying the circuit using serial parallel reductions. We begin by noting that R3 and R4 are connected in parallel with an equivalent resistance of R equivalent 1 equals to R3 times R4 over R3 plus R4. Now we notice that R equivalent 1 is connected in series with R2 with an equivalent resistance of R equivalent 2, which equals to the sum of both resistors. The resistance between nodes A and G is equal to the equivalent resistance of the parallelly connected resistors R1 and R equivalent 2, where RAG equals to R1 times R equivalent 2 over R1 plus R equivalent 2 equals to 3.2 ohms. The voltage between nodes A and G is equal to I times RAG equals to 32 volts. This is the voltage across R equivalent 2, from which we can find the current flowing through R equivalent 2, where I dot equals to VAG over R equivalent 2 equals to 8 amps. In order to find the power dissipated in R4, we need to find the current flowing through R4, and in order to do that, we need to find the voltage across R4, that is VBG. By applying KVL on this loop, we notice that VAG is equal to VAB plus VBG, from which VBG equals to VAG minus VAB equals to 32 minus I dot times R2 equals to 19.2 volts. This is the voltage across R4, from which the current flowing in R4 equals to VBG over R4 equals to 3.2 amps. The power dissipated in R4 equals to the current flowing in R4 squared times R4 equals to 61.44 watts. In problem 1, we need to find the equivalent resistance between nodes A and B. We start by noting that R2 is connected in parallel with R4, from which the equivalent resistance of R2 and R4 is given by R equivalent equals to R2 R4 over R2 plus R4 equals to 4.8 ohms. This equivalent resistance will be in series with R1 and R3, from which the equivalent resistance between nodes A and B, which is RAB, equals to R1 plus R equivalent plus R3 equals to 15 ohms. In problem 2, and like problem 1, we need to find the equivalent resistance between nodes A and B. We start our solution by noting that R4, R5, and R6 are connected in parallel. Their equivalent resistance is given by R equivalent 1, which equals to 1 over R4 plus 1 over R5 plus 1 over R6 to the power minus 1, equals to 24 ohms. R3 is in series with R equivalent 1. Their equivalent resistance is R equivalent 2, which equals to R3 plus R equivalent 1 equals to 40 ohms. R1 is in parallel with R2 with an equivalent resistance of R equivalent 3 equals to 40 ohms. Now R equivalent 3 and R equivalent 2 are connected in parallel, from which the resistance between nodes A and B, RAB, equals to R equivalent 2 times R equivalent 3 over R equivalent 2 plus R equivalent 3 equals to 20 ohms. In this example, we need to find VG, knowing that the voltage across R6 equals to 20 volts. We begin our solution by noting that R5 is connected in series with R6 with an equivalent resistance of R equivalent 1, which equals to R5 plus R6. We also notice that R2 is connected in parallel with R4 with an equivalent resistance of R equivalent 2 equals to R2 times R4 over R2 plus R4. The current flowing in R6 is the same as the current flowing in R equivalent 1, where I equivalent 1 equals to the voltage across R6 over R6 equals to 4 amps, from which the voltage across R equivalent 1 equals to the current flowing in R equivalent 1 times R equivalent 1 equals to 80 volts. Now we notice that R equivalent 2 is connected in parallel with R equivalent 1 with an equivalent resistance of R equivalent 3 equals to R equivalent 1 times R equivalent 2 over R equivalent 1 plus R equivalent 2. VAG is the voltage across R equivalent 3, from which we can find the current flowing in the loop, where I equals to VAG over R equivalent 3. Applying KVL on this loop, we find that VG equals to I times R1 plus VAG plus I times R3 equals to 126 volts. In this problem, we need to find I dot and Ij. We begin our solution by noting that R6 is connected in series with R7 and that their equivalent resistance is connected in parallel with R8. We also notice that R1, R2, R3 are connected in series. The equivalent resistance of R6, R7, and R8 is given by R equivalent 1 equals to R8 times R6 plus R7 over R8 plus R6 plus R7. R5 is in series with R equivalent 1, where R equivalent 2 equals to the sum of both equals to R5 plus R equivalent 1. R1, R2, and R3 are in series with R equivalent 3 equals to R1 plus R2 plus R3 equals to 200 ohms. Now, R equivalent 2 and R equivalent 3 are in parallel with an equivalent resistance of R equivalent 4 equals to R equivalent 2 times R equivalent 3 over R equivalent 2 plus R equivalent 3. Now we can find Ij from this simplified circuit, where Ij equals to V over R equivalent 4 plus R4 equals to 12 amps. The voltage between nodes A and B is given by Ig times R equivalent 4 equals to 480 volts. In order to find the current I dot, we need to find the voltage across R equivalent 2. Before doing that, we need to find the current flowing in these two resistors, where I equals to VAB over R5 plus R equivalent 2 equals to 9.6 amps. The voltage across R equivalent 2 can be found by applying KVL on the loop, from which we find that VAB equals to VAC plus VCB. which yields that VCB equals to VAB minus VAC equals to VAB minus I times R5 equals to 153.6 volts, from which I dot equals to VCB over R6 plus R7 equals to 1.92 amps. In this problem, we need to find V out. We start our solution by noting that there is an open circuit between the 1 kilo ohm and 5 kilo ohm resistors, which means that there is no current flowing in either of these resistors, and hence there is no voltage drop across any of these resistors, from which the voltage at point B is equal to the voltage at node A, and the voltage at point D is equal to the voltage at node C. We also notice that R1 and R2 are connected in series with an equivalent resistance of R equivalent 1 equals to the sum of both. Also, R3 is connected in series with R4 with an equivalent resistance of R equivalent 2, which equals to the sum of both. This is a current divider circuit where I1 equals to I times R equivalent 2 over R equivalent 1 plus R equivalent 2, and I2 equals to I times R equivalent 1 over R equivalent 1 plus R equivalent 2. We can find the voltage difference between nodes A and C by finding the voltage difference between each of these nodes and a common node like node E. VAE equals to I1 times R2 and VCE equals to I2 times R4, from which V out equals to the voltage difference between points B and D is equal to the voltage difference between nodes A and C, which equals to VAE minus VCE equals to minus 2.7 volts. We can also solve this problem by choosing another common node between nodes A and C. In this case, let it be node F, from which VAF equals to minus I1 times R1 and VCF equals to minus I2 times R3, from which V out equals to VAC equals to VAF minus VCF equals to minus 2.7 volts, which is the previous answer that we got with the common node E. Please feel free to contact me with any questions, suggestions, or corrections. Thank you.